Today what I want to do is talk about some fundamental concepts to the SUNA. Specifically, I want to talk about thermal energy, heat, temperature, and what those mean. The overall goal is to make sure that you can use these terms correctly to describe what is happening to energy and particles within a system. We are supposed to be doing the solar cooker thing tomorrow. We might have to just wait and see what the weather is going to be like. If we get the kind of snow that is forecasted, we might end up having to shovel out our projects. So we'll just see what it's like. We'll see if everybody can get in tomorrow. Hi. I'll take money. I have no problem taking people's money. Thank you. So, we have talked about the states of matter in the past, solids and liquids and gases. There's actually more than 3 states of matter. There's 5. Do you know what the other 2 are? Have you heard of the term plasma? Okay, so plasma is the 4th state, and then the condensate is the 5th state. It's a theoretical construct. We're only going to focus on solids, liquids, and gases in Physical Science 20, and actually for high school science in general. These are some of the things that we've talked about in terms of particle behavior in solids and liquids and gases. So if you can imagine an ice cube is made up of water particles that are closely packed together. I'm just going to put up a Java simulation here to show you how the particles change as heat is added to it. If you look at the water particles on the screen, what kind of motion do they have? Okay, so they are moving, even though they are in an ice cube. However, thankfully, they're not moving to the extent where the ice cubes start walking around the freezer or something strange like that. So this is what we call vibrational motion. If I add heat to this, what's going to happen to the movement of the particles? Okay, so you can see that they are moving faster. And now eventually, do you see what kind of motion they have now? They're not just vibrating anymore. So let's pull this down so they get back into the liquid state here. All right. So right here, the particles are only vibrating. When we add heat and they start going into a liquid phase, they gain a new type of motion. Trying not to warm it up too much. There we go. The particle on the left-hand side that's above the others has that new type of motion. So not only is that water particle vibrating, it's also turning around. So all liquid particles have vibrational motion and rotational motion. If I heat this sample up even more, and it starts escaping into the gas phase, the particles exhibit a 3rd type of motion. They are vibrating, they are rotating, but they also start traveling in straight lines until they collide with something else. And then it's almost like they ricochet off of that substance. Because of that movement, we see interesting things happen to the properties of solids, liquids, and gases. If things are only vibrating, and they're not rotating or traveling in straight lines, that means we're going to be able to pack more of those particles closer together. When those particles start to vibrate and to turn around, they have more kinetic energy, which means that they're going to take up more space. They're going to start hitting their neighbors and pushing their neighbors away a little bit. Gases have the most energy. What's really interesting is that substances have their own unique melting points, which is when the substance goes from a solid to a liquid, and their own evaporation or boiling points, which is when something goes from a liquid to a gas. For example, something such as oxygen is a gas state at even a very, very cold temperature, versus water, it's not until it's 100 degrees Celsius. It has to do with these attractions between particles. The harder it is to break attractions between particles, the harder it is to start rotating, and the harder it is to start traveling in straight lines. As we go through senior high science, and we start to learn more about the forces that attract different particles together, we'll learn more about how the structure at an atomic level actually influences why something is a solid, why something is very dense or not very dense. Why does something have a high viscosity? It actually always comes back to the particle theory. In my coffee cup, I have some nice hot water predominantly with some coffee in it as I brewed it here. These red and black things represent water particles here. So if I talk about thermal energy, I'm actually talking about two things. I'm talking about how much movement each particle in this coffee cup has. Let's say that I drink some of this coffee, and now I only have this much coffee left in my coffee mug. What happens to my total thermal energy? Let's say the coffee is still the same temperature. The particles are still moving at the same speed. But I've consumed half of my coffee. Is my thermal energy going to go up, go down, or stay the same? It's going to go down because the number of particles has changed. If I were to put that half cup of coffee into the microwave and heat it up, well then I'm making the particles go faster, so I'm actually increasing the thermal energy. If it's a Saturday, I'm probably going to forget that coffee cup in the microwave and it's going to cool down. What happens to particle movement when a substance cools down? It goes slower, so the total thermal energy is actually going to decrease. So when I talk about thermal energy, I'm talking about how fast all of the particles in that substance are moving. I can change that by adding or removing particles, or by making those particles go by faster or slower. So you picked up those pretty fast. Let's try this one. Do you think an ice cube has thermal energy? When you're asking yourself if something has thermal energy, there's actually two questions you have to ask yourself. Are there any particles in ice? Absolutely. Otherwise, we wouldn't have anything. Do you think particles in ice move? Well, let's go back to this Java back here. And I'm going to cool this sample down. And I'm going to bring it down to 273 Kelvin, which is equal to 0 degrees Celsius. Whoops, a little bit too fast. Okay. So this would be water in a solid state. Do those particles have motion? Absolutely. The correct answer to this question is yes. An ice cube does have thermal energy because an ice cube is made up of particles and those particles are moving. An ice cube does not have a great capacity to transfer heat, though, because the particles are moving relatively slowly. So I've given you two examples. I've given you the coffee example, and I've given you the ice example. So what if I put the two together like this and said, which one do you think has more thermal energy? A cup of coffee, for example, what's sitting out in front of you, or an iceberg? An iceberg actually has more thermal energy. Are the particles in an iceberg moving faster or slower than a hot cup of coffee? Much slower. Then how is it possible for an iceberg to have more thermal energy than a cup of coffee? Just about. Anybody seen an iceberg? They can be as large as your house. Lots and lots of water particles are trapped within the iceberg structure. So it actually has quite a bit of thermal energy. So the property of thermal energy is dependent on how fast particles are moving, but also how many particles there are. Heat is generally something that we feel. It's really nice sitting up here on a cold morning because this is where the radiator is, and the heat energy is coming off of the radiator. To represent heat, we use the letter Q. We do not use the letter H for heat because H is already used to represent other things in science. A lowercase h is used to represent height. For example, if you decide to go on into Physics 30, you'll talk about potential energy. That's mass times 9.81 meters per second squared times height. You'll have small h in that formula. Capital H is enthalpy, which is something that is totally different than heat. And that is a chemistry term. Depending on where we get it to in the unit, we may or may not have a chance to talk about enthalpy. Heat is transferred. What are the three ways in which heat can be transferred? Conduction. Excellent. Conduction happens in solids where particles are in contact with each other. Convection happens in fluids, that's your liquids and your gases, and radiation generally happens, well, it can be through the air, but it also can be through space. Okay, so for example, that is how the Earth is heated, it's through the radiation from the sun. Heat is a transfer of thermal energy. So we can represent that mathematically using the letters. ETH is the symbol for thermal energy. This is the mathematical symbol for delta. Do you remember what delta means? Okay, what if I gave you an example of doing a speed measurement in Science 10 or you had delta D divided by delta T? No, not ringing the bell. We practiced this already. Final temperature minus initial temperature gives you your change in temperature. Whenever you see the triangle symbol, it means change. When you calculate change, you always must go final minus initial. The reason is, it is possible to get a positive number. It's also possible to get a negative number. Let's say you calculate your change in thermal energy, and it is a positive number. Has the substance gained heat energy, or has the substance lost heat energy? Let's put it in the context of temperature then. If I was at 25 degrees Celsius at the end of my experiment, and I started at 15 degrees Celsius at the beginning of the experiment, I have a change of positive 10 degrees Celsius. Has my temperature increased or has my temperature decreased? It's increased. So if you have a positive delta, that means that whatever the change is, it has increased. If you decrease thermal energy, that means that the system has lost thermal energy to something else. Temperature is the third concept. Temperature is a measurement of how fast the particles are moving in a substance. Suppose this is a thermometer. How is it possible that the liquid that is inside the thermometer goes up and down that thermometer to give us a temperature reading? Okay, so in thermometers we generally have alcohol, and that alcohol, like anything, is made up of particles. If we add heat to those particles, what happens to the movement of the particles? It moves faster, and when things move faster, there's more collisions, and it takes up space. The liquid expands when it's heated because the particles are moving faster, and it takes up more space. Think about the opposite. We put the thermometer out right now. It's cooler outside. The particles are going to slow down. Fewer collisions, which means they take up less space. Here's an example. So if I cool this substance down, you see here that the particles are moving very, very fast. So they're not colliding with each other with a whole lot of energy. Versus if I take this and increase the temperature, we see that the particles are moving faster. They could collide with more energy, and those particles physically take up more space. Do you remember in Science 7 we talked about 3 different temperature scales? I know that's a long time ago. We use Celsius in Canada. Have you heard of the temperature scale Kelvin? Okay. That's the scale we tend to use in science because it is a Système International unit. Fahrenheit? Do one of your grandparents talk in Fahrenheit? Mine did all the time because they spent half the year in Arizona. So I was like, oh, it's 65 degrees out today. You're definitely talking about a Fahrenheit scale because if it was 65 degrees Celsius, holy smokes. Rankine is not heard about as much. It is based on the Fahrenheit scale, but it uses absolute zero as its zero value as well. This is generally used in engineering, so Stefan, you might be working with the Rankine scale in the future. Yeah. So we have to be able to know how to go from Celsius to Kelvin and how to go from Kelvin to Celsius. 1 degree Celsius is equal to 1 degree Kelvin, which is nice. That means that if it increases by 10 degrees Celsius, it also increases by 10 degrees Kelvin. That is not the case with the Celsius and the Fahrenheit scale. 1 degree Celsius is not the same as 1 degree Fahrenheit. Now, if I can go back to this previous slide for a moment. If you take a look at these first two thermometers, which is the scales we're concerned about right now, Kelvin starts at 0 down here, and 0 is when the molecular motion ceases to be theoretically. This is equal to minus 273 degrees Celsius. Any suggestions on how we can find the Kelvin temperature for today's temperature, which is minus 6? How about we do this? So 0 Kelvin is equal to minus 273.15 degrees Celsius. Let's say it's minus 6 degrees Celsius out here. And I need to figure out how many Kelvin that is. There's a couple ways we can figure this out. Remember that 1 degree Celsius is equal to 1 degree Kelvin. How many degrees Celsius have I increased the temperature by? What is the change in temperature? Temperature has changed by 267.15 degrees Celsius. If this is increasing by 267.15 degrees Celsius, then this temperature is also going to increase by the value of 267.15. The reason I know this is because a 1 degree Celsius increase is also a 1 degree Kelvin increase. In order to go from degrees Celsius and change that number into Kelvin, we must add 273.15. If the question is asking us to go from Kelvin to degrees Celsius, we do the opposite mathematical operation, and we subtract 273.15. In terms of when do you use Celsius and when do you use Kelvin, honestly, it depends on what formula you're using. For example, one of the first formulas that I'm going to be showing you is Q equals MC delta T. And this delta T has to be in degrees Celsius. And the reason why that has to be in degrees Celsius is because the standards that we use for C are in joules per gram degrees Celsius. So you have to be consistent with your temperature units. However, in a chemistry formula that uses the ideal gas law, which is PV equals nRT, in this case, temperature is going to be expressed in Kelvin. And the reason why it's going to be expressed in Kelvin is because this standard, which was 8.3 something 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 over, okay, so it's going to be and in this case, the standard uses Kelvin, which means that our temperature that we put into that formula has to match those temperature units. As we go through Physical Science 20, I will be very clear about whether or not you have to use degrees Celsius in a formula or if you have to use Kelvin in a formula. What you have to be able to do right now is if I gave you a number in degrees Celsius, you would be able to change that value into Kelvin or vice versa. We're going to do a few practice questions. You're welcome. Okay. You are going to be doing question numbers 1 to 6, but when you get to question numbers 5 and 6, we're not doing all parts. So in question 5, I only want you to do A and B. When you do question number 6, only A and B as well. We're not using the Fahrenheit scale in Physical Science 20. If you would like to know how to do those temperature conversions, I'm more than willing to teach you. However, it's not something that you're going to be using in this course, so I'd rather occupy the brain space with something else.